Welcome back, everyone. We're diving into a topic today that a lot of you have been requesting algorithms. And to really get into it, we're using excerpts that you sent us from the Introduction to Algorithms textbook.
Ah, classic.
Really is.
Yeah.
So I think the first question on everyone's mind is, what are they really? Because we hear about algorithms all the time these days.
Right.
But why? Why should we care? What's the big deal?
Well, an algorithm, it's basically a set of instructions to solve a problem. If you think about it, it's kind of like a recipe. You have your ingredients and you have the steps and the order you have to do them in to get to, that delicious outcome.
Okay, so it's not like some super complicated code that only geniuses can understand.
Not at all, no. In fact, we use algorithms every day without even realizing it.
Really?
Yeah. I mean, think about it. You sort your laundry or you find the shortest route to work or even just making a sandwich. I mean, these all involve some kind of algorithmic thinking.
Oh, that's pretty interesting. So the book spends a lot of time talking about sorting algorithms. What's so important about sorting in computer science?
Sorting is foundational. I mean, it's
Right.
everywhere. It's from organizing files on your computer to searching for information online. And efficient sorting algorithms, they make all of these tasks just lightning fast.
Makes sense. So there are two sorting algorithms specifically mentioned in the book: insertion sort and merge sort.
Hmm.
What's the difference between those?
Okay, so imagine you're sorting a deck of cards.
Right.
Insertion sort is kind of like when you arrange the cards in your hand one by one, inserting each new card into its right spot.
Okay.
Merge sort, on the other hand, it's like you divide the deck into smaller piles, sort each pile, and then merge them back together in order.
Oh, so merge sort is kind of like a divide and conquer strategy.
Exactly. Yeah, exactly. And it's a bit more complex than insertion sort, but it's much more efficient when you're dealing with large data sets.
Okay, that makes a lot of sense. So that kind of brings us to this concept of big O notation, which I think is, how programmers measure an algorithm's efficiency. Is that right?
Exactly. Yeah, big O notation, it looks at how an algorithm's running time, increases as the input size grows.
So if I'm sorting like 10 numbers, it doesn't really matter which algorithm I use, but if I'm sorting like, millions or billions.
Then the choice of algorithm becomes super important. Insertion sort, for example, has a big O of n squared, meaning that it becomes really slow as the input size increases. The running time grows quadratically.
Quadratically. So the bigger the input gets, the worse it performs.
Yeah, pretty much. Now, merge sort, which we talked about before, has a big O of n log n, which means that it's way more efficient for those, really large data sets.
So merge sort is like the champion when we're talking about big data.
You could say that. But it's important to remember that big O notation really focuses on that worst case scenario. Sometimes an algorithm might perform better than its big O suggests, depending on the specific input that you give it.
So it's not the whole story.
Right. It's definitely a crucial part of understanding an algorithm, but, there are other factors to consider, and we even have other notations like big omega and big theta to give us a more complete picture.
So what are those?
Well, big omega, it looks at the best case scenario, so it's kind of the opposite of big O.
Okay.
And big theta, it tells us that an algorithm's performance is kind of tightly bound between its upper and lower limits. It's a bit more precise.
So we have a whole family of big notations. Can you give me an example of how these notations actually work in practice?
Sure. Let's go back to insertion sort that we were talking about before. So its worst case performance, as we said, is big O of n squared. But if the input is already sorted, its best case performance is actually big omega of n.
So insertion sort, it can be both big omega of n a n d, big O of n squared. That's pretty interesting.
Yeah. And that just highlights how important it is to look at the context, and the potential range of an algorithm's behavior. And speaking of efficiency, the book also delves into this powerful algorithmic paradigm called divide and conquer.
And merge sort is a good example of that, right?
Exactly. The idea is to break down a complex problem into smaller, kind of self-similar subproblems. You solve those recursively, and then combine the solutions to get your final answer.
It's like breaking down a giant puzzle into smaller pieces, solving each piece, and then putting it all back together.
Yeah, perfect analogy. And this approach, it's used everywhere, from searching and sorting to things like artificial intelligence.
Okay, that makes sense. Now, the book also mentions these concepts of probabilistic analysis and randomized algorithms. Those sound Those sound a bit less predictable.
They do, but they're incredibly valuable tools. Probabilistic analysis, it helps us understand the average case performance of an algorithm when the input follows a certain probability distribution.
So instead of just looking at the worst case or best case scenario, we're considering what's likely to happen on average.
Exactly. Imagine, you're trying to hire the best candidate for a job and you have N applicants. They're coming in random order. You don't have to interview every single person.
Oh, thank goodness. Interviewing hundreds of people would be exhausting.
Right. So probabilistic analysis can help us, find that sweet spot, a strategy that balances the number of interviews with the chances of actually finding the best candidate.
Wow. So algorithms can help us make smarter decisions even when there's randomness involved.
Absolutely. And then we have these things called randomized algorithms, which actually incorporate randomness internally, as part of their process to achieve better performance.
Okay, so give me an example. Like, how would you use a randomized algorithm?
Think about shuffling a deck of cards. Or, in more formal terms, shuffling an array randomly using an algorithm called permute by sorting. It uses randomness to guarantee that the outcome is truly shuffled.
So it's like having a digital dealer that's completely fair and unpredictable.
Exactly. Randomized algorithms, they're used everywhere, from cryptography to machine learning. They're pretty versatile.
So algorithms, they can sort, they can search, they can help us make decisions, they can shuffle. I mean, it's pretty incredible.
Yeah, and that's just scratching the surface. The applications of algorithms are vast. I mean, they're really everywhere.
Okay, so let's talk about those applications. Like, where do algorithms really shine in our everyday lives?
Well, they're all around us. Think about searching for information online. I mean, search engines use incredibly sophisticated algorithms to index like billions of web pages, rank the results, and then deliver the most relevant information to you like in milliseconds.
It's true. It's amazing how fast it is. I never really think about, what's happening behind the scenes, all the algorithmic magic that's going on.
Right. It's pretty mind-boggling when you think about it. And it's not just search engines either. I mean, algorithms are crucial for things like, finding the shortest route on a map, using a navigation app,
Right.
or compressing data to save storage space on your phone or computer,
Oh, yeah.
even personalizing your social media feeds. I mean, it's really everywhere.
Yeah. So algorithms they're kind of running the world.
In many ways, yeah, you could say that. They're the invisible force behind so much of what we do and experience in our digital lives.
You mentioned bubble sort before, which is another sorting algorithm, right? Is it like a faster version of insertion sort?
Not quite. It turns out that bubble sort is actually quite inefficient, especially when you're dealing with large data sets. It has a big O notation of n squared, just like insertion sort. But in practice, it tends to be even slower.
So why do people even use bubble sort then, if it's so inefficient?
Well, it's really simple to understand and implement, which makes it kind of a popular choice for teaching beginners about sorting algorithms. But when it comes to real world applications, where efficiency is really important, there are almost always better options out there.
Okay, that makes sense. So back to those advanced topics we touched on earlier. You mentioned Fibonacci heaps and B trees. What are those used for?
Those are specialized data structures, and they're designed to optimize very specific tasks. So Fibonacci heaps, they're known for their efficiency in operations like finding the minimum value in a set of data, and that's used in algorithms for things like finding the shortest path in a graph, which is essential for navigation apps like we were talking about before. And then B trees, they're specifically designed for managing data that's stored on disk drives, because accessing information on a disk drive it's much slower than accessing information in the computer's main memory. So B trees help to minimize those slow disk accesses and make data retrieval much faster.
So if I'm working with like massive data sets that are stored on a hard drive, then B trees are my best friend.
They could be, yeah. They're used extensively in databases and file systems, so they help us manage, just huge amounts of data efficiently.
Wow. It's amazing to think about how these, seemingly abstract concepts actually have like real concrete applications that impact us every day.
Exactly. And it really highlights why understanding algorithms is so crucial in today's world. It's not just about becoming a programmer. It's about developing like a deeper understanding of how things work, the forces that are shaping our digital landscape.
It's like having this superpower, this ability to see the code behind the curtain.
Right.
But speaking of mind-boggling concepts,
Yeah.
the textbook also mentioned something called P versus NP problems. Is this something I need to worry about?
That's a question that has puzzled computer scientists for decades. I mean, it's one of the biggest unsolved mysteries in the entire field. And
Yeah.
and essentially what it asks is every problem whose solution can be quickly verified can also be quickly solved.
Okay, can you give me an example? Because I'm having trouble wrapping my head around that.
Sure. So imagine you're trying to solve a Sudoku puzzle, right?
Okay.
It's pretty easy to check if a completed puzzle is correct. You just have to make sure that every row, column, and box has the numbers 1 through 9 without any repetitions.
Right.
But finding the solution in the first place, that can be quite challenging.
Okay, that makes sense. So
Yeah.
so P problems are like the ones we can solve easily,
Mm-hmm.
and then NP problems are the ones that make us want to pull our hair out.
Well, P stands for polynomial time, which means that the time to solve the problem, it grows at a manageable rate as the input size increases.
Okay.
But NP stands for non-deterministic polynomial time, which, without getting too technical, means we don't currently have any efficient algorithms to solve those problems when the input size gets really large.
So the million-dollar question is, are P and NP the same thing? Like, could we one day find those efficient solutions for those really tricky NP problems?
That is the holy grail of computer science. And if P does equal NP, it would have huge implications for so many fields. I mean, imagine being able to, crack the toughest encryption codes or optimize, complex logistical problems in the blink of an eye. But for now, the answer remains a mystery.
So it's still out there.
It is. It's a big question mark.
I have a feeling this is a question that's going to keep computer scientists busy for a long time to come.
Yeah.
Well, this deep dive has been an absolute eye-opener. We've explored, the world of algorithms from these basic sorting techniques to the complexities of big O notation. We even delved into, advanced concepts like Fibonacci heaps and B trees, and even got a glimpse of these mysterious P versus NP problems.
It really has been quite a journey. And before we wrap up, there's one more concept from the textbook that I think is worth highlighting. It's called amortized analysis.
Amortized analysis. Okay, that sounds a little intimidating. What is that all about?
It's actually not as complex as it sounds. Amortized analysis, it's basically a way of analyzing the performance of algorithms, but instead of focusing on just a single operation, we look at a sequence of operations.
So instead of looking at the worst case time for one operation, we're kind of considering the average cost over
Yeah.
a series of operations.
Precisely. It's kind of like saying, hey, even if this one operation is a bit expensive, it's balanced out by the efficiency of the other operations in that sequence.
Can you give me an example? I always find it easier to understand these things with like a real world scenario.
Sure. Imagine you have a dynamic array, right? And it grows as you add elements to it.
Okay.
Now, occasionally you might need to resize that array, which can be a pretty time-consuming operation.
Right.
But amortized analysis tells us that the cost of those, occasional resizings, it's actually spread out over all of the insertions that you're doing. So the average cost per insertion, it actually remains relatively low.
So it's kind of like we're paying off the cost of those expensive operations over time with the savings from the cheaper ones.
Exactly. It's a great way to think about it. And amortized analysis, it's really useful for understanding the true performance of algorithms that involve, these dynamic data structures or a series of operations where the costs might vary. It gives you a more holistic view of the efficiency.
This deep dive has been absolutely incredible. We've explored the world of algorithms from those basic sorting techniques to the complexities of big O notation, amortized analysis, and even touched on those mind-boggling mysteries of P versus NP problems. It's amazing. I feel like I've gained a whole new level of understanding and appreciation for these kind of invisible forces that are shaping our digital world.
It's been a real pleasure diving into this fascinating topic with you. And remember, this is just the beginning, right? The world of algorithms, it's vast, it's constantly evolving. There's always more to learn and explore. And who knows, maybe you'll be the one to make the next groundbreaking discovery in the world of algorithms.
I'm definitely feeling inspired to to keep exploring. To our amazing listener out there, thank you so much for joining us on this deep dive into the fascinating world of algorithms. We hope you found it as insightful and as engaging as we did. And remember, keep that curiosity burning. Never stop exploring. And until next time, happy coding.